In the previous section, we transferred latest data between the host and FPGA using programmatic front panel communication. By the end of this module, you will be able to develop a host VI on the RT target that communicates with the FPGA VI. Let's talk a little bit about the FPGA architecture with LabVIEW RealTime. So if we look at this graphic, we've talked about it already before. Let's look at the real-time system block. Okay, so let's say we have an FPGA on there, and then we would need to develop a host VI that's running on the LabVIEW RealTime target to communicate with the FPGA VI. So for example, if this was a cRIO, then you'd need something running on the RT OS of the cRIO to communicate with the FPGA VI. Or if this was a PXI system, you might have a R series board in the PXI system, and the PXI is running in real-time operating system. You might need a host on that PXI that's communicating with the FPGA VI. In this section, we'll give a quick overview and introduction to real-time. So what are the advantages of using a real-time host versus a Windows host? So code execution on a real-time host is going to be more deterministic than a Windows OS. Okay, so what that means is the code that's running on an RT target is going to have much less jitter than something that's running on Windows, and you're going to be able to more predictably know how long the code execution time is going to take. Also, you get the ability to set tasks to run at different priorities, including a time-critical priority. And that ability is going to allow you to separate deterministic tasks from non-deterministic tasks in your application. So if you have some critical code, you can make that into a deterministic task and have that running at a very high priority. Also, real-time OS, because it's more pared down, is going to be more stable than a Windows OS. Also, real-time targets have a 1 megahertz clock, while Windows has a 1 kilohertz clock. So on a real-time target, in those VIs, you can actually get microsecond resolution, and Windows, you can only get millisecond resolution. So what are some common tasks that you would have running on your RT host VI? So one, you can do some data processing. So if you have some heavy-duty data processing that doesn't need to happen super fast, you can have that happening on your RT target instead of your FPGA. Also, you can perform some operations that are not available on your FPGA target. So for example, doing file logging and things like that. Also, you might want to do double precision floating point math on your RT target because that's not supported on your FPGA target. You might want to sequence multiple FPGA VIs. Again, like I said, you can log data, run multiple VIs. You can also control the timing and sequencing of your data transfer. So from your RT host, you can send commands to your FPGA and try to sequence things on your FPGA VI. Also, you could potentially also coordinate operation of several FPGA targets. So let's say you have a RT target that's a PXI, and within that PXI, there's multiple R series boards. Well, you can use the RT host VI to control communication and the sequencing and just the operation of several FPGA targets in that case. Namely, in this case, we have several R series boards. You can also coordinate the operation of those FPGA targets with other measurement devices. So maybe that PXI also has a DAC card, or maybe it also has an arbitrary waveform generator and things like that. Also, the RT host is going to be able to communicate with the Windows UI. So the FPGA VI can communicate with the RT host VI, which does some things, and then the RT host VI can send relevant information back up to a Windows VI to give the application a user interface. So if you want to get more information on real-time, you can take the LabVIEW RealTime One course. And in this course, you'll learn how to configure real-time hardware. You'll talk about different architectures and concepts, like with priorities and things like that. You can learn how to improve your determinism of your application in real time. You can set priorities of different processes. You'll be able to learn how to pass data between multiple loops on your real-time target. You'll also talk about doing network communication. So how do you communicate with a Windows host VI from your RT target VI? We'll also talk about different things like shared variables with RT FIFO as a method of transferring data. We'll talk about network streams, which is a great way of transferring buffered data between your RT VI and your Windows VI. And there's also another communication method called network publish shared variables. And we'll talk about much more in that class. So if you are using a RT target, I highly recommend learning the principles that are covered in this course. So if you're using a compact RIO that's going to have a RT OS on it, definitely learn more about real-time for that. Or if you have a PXI that's running a real-time OS. So how would you develop a RT host VI? So you go to your project, you would right-click your RT target. In this case, it's a CREO 9074. Go to New, and then select VI. And that VI will run on your RT target. So when you're developing an RT host VI, it's going to be very similar to what we talked about in a previous module. So you'll use the FPGA interface functions, just like we did before. So on your RT host VI, you would have the open FPGA VI reference, and that's where you would select which FPGA VI you want to communicate with. And then you'll do the write read control for latest values. You can use methods, and you can also close that FPGA reference. So these FPGA interface functions are pretty much used the same way, whether you're using a Windows host VI or a RT host VI. So after you're done developing an RT host VI, when you hit the run button, you'll get a deploying status window. And what's happening here is it's deploying it to your RT target, and at that point, that code that you developed on your development computer is going to be deployed to your RT target and running on your RT target. Let's talk a little bit about front panel communication in LabVIEW RealTime. So when you're developing a RealTime VI, you're actually developing it on your host computer, which is running Windows, right? So what you'll do is when you hit the run button on your host computer for your RT VI, it'll go ahead and deploy that code to your RT target. So if we look at the bottom there, pretty much the functionality that you've defined in your block diagram, that logic is actually running on your RT target. But on your host computer, you still have that front panel open, and what's going on behind the scenes is there's some user interface communication that's going on. So even though the code is running on your RT target, there's some code behind the scenes that is going up to your host computer and automatically updating your controls and indicators with values that are coming from your RT target VI. Okay, so this is kind of similar to what we saw with FPGA when we talked about interactive front panel communication. This is kind of the same thing except for the real-time VI. So when should you use front panel communication for LabVIEW RealTime? Well, the advantage is it's easy to debug VIs, just kind of like we saw with the FPGA interactive front panel communication. You're able to quickly develop a RT VI and then run it, deploy it to your RT target, and then you're able to use the controls and indicators and make sure everything's working all right. You can use debugging tools like highlight execution and things like that. So it's a great way to debug VIs or quickly monitor them during development. However, when you're creating your final application, you don't want to rely on using this interactive front panel communication. What you want to do is you want to prepare your RT application as a final application that you can deploy and have it stay on the RT target. So you'll learn how to build a proper final RT application in the LabVIEW RealTime One course, but we won't get into it in the FPGA course. Now you can develop a host VI on the RT target that communicates with the FPGA VI. Next, we will develop a Windows VI on a PC that acts as a user interface and communicates with the host VI on the RT target.